It's odd, but in the infrequent occasions when I've been called upon in a formal place to play the bongo drums, the introducer never seems to find it necessary to mention that I also do theoretical physics. I believe that's probably that we respect the arts more than the sciences. The artists of the Renaissance said that man's main concern should be for man. And yet, there are some other things of interest in the world. Even the artists appreciate sunsets and the ocean waves and the march of the stars across the heavens. And there is some reason then to talk of other things sometimes. As we look into these things, we get an aesthetic pleasure from them directly on observation. But there's also a rhythm and a pattern between the phenomena of nature, which isn't apparent to the eye, but only to the eye of analysis. And it's these rhythms and patterns which we call physical laws. What I want to talk about in this series of lectures is the general characteristics of these physical laws. That's even another level, if you will, of higher generality over the laws themselves. And it's really, all I am talking about is nature as seen as a result of detailed analysis. But only the most overall general qualities of nature is what I mainly wish to speak about. Now, such a topic has a tendency to become too philosophical because it becomes so general that a person talks in such generalities that everybody can understand him, and it's considered to be some deep philosophy. However, I would like to be rather more special, and I would like to be understood in an honest way rather than in a vague way to some extent. And so, if you don't mind, I'm going to try to give, instead of only the generalities, in this first lecture, an example of physical law, so that you have at least one example of the things about which I'm speaking generally. In this way, I can use this example again and again to give an instance to make a reality out of something which would otherwise be too abstract. Now, I've chosen for my special example of physical law to tell you about the theory of gravitation, or the phenomena of gravity. Why I chose gravity, I don't know. Whatever I chose, you would have asked the same question. Actually, it was one of the first great laws to be discovered, and it has an interesting history. You might say, yes, but then it's old hat. I would like to hear something about science, more modern science. More recent, perhaps, but not more modern. Modern science is exactly in the same tradition as the discoveries of the law of gravitation. It is only more recent discoveries that we would be talking about. And so I do not feel at all bad about telling you of the law of gravitation, because I am, in describing its history and the methods, the character of its discovery and its quality, talking about modern science, completely modern. This law has been called the greatest generalization achieved by the human mind. And you can get already from my introduction, I'm more interested not so much in the human mind as in the marvel of nature who can obey such an elegant and simple law as this law of gravitation. So our main concentration will not be on how clever we are to have found it all out, but on how clever she is to pay attention to it. Now, what is this law of gravitation that we're going to talk about? The law is that two bodies or bodies exert a force upon each other, which is inversely as the square of the distance between them and varies directly as the product of their masses. And mathematically, we can write that great law down in the formula, some kind of a constant times the product of the two masses divided by the square of the distance. Now, if I add the remark that a body reacts to a force by accelerating or by changing its velocity every second to an extent inversely as its mass. It reacts, it changes velocity more if the mass is lower and so on, inversely as the mass. Then I have said everything about the law of gravitation that needs to be said. Everything else is a consequence, a mathematical consequence of those two things that I said. That's a remarkable enough phenomenon in itself that the next lecture will consider this in more detail. Now, I know you're not all here. I know some of you are, but you're not all mathematicians, and so you cannot all immediately see all of the consequences of these two remarks. And so what I would like to do in this lecture is to briefly tell you the story of the discovery, tell you what some of the consequences are, what the effect of this discovery had on the history of science, what kinds of mysteries such a law entails, something about the refinements made by Einstein, and possibly the relation to other laws of physics. The history of the thing, briefly, is this, that the ancients first observed the way the planets seemed to move about in the sky and concluded that they all went around, along with the Earth, went around the sun. This discovery was later made independently by Copernicus after they had forgotten that, people had forgotten that it had already been made. Now, the next question that came up to study was exactly how do they go around the sun? That is, exactly what kind of motion? Do they go with the sun at the center of a circle, or do they go in some other kind of a curve? How fast do they move, and so on? And this discovery took a longer to make. The times after Copernicus were times in which there were great debates about whether the planets in fact went around the sun along with the Earth, or whether the Earth was at the center of the universe, and so on. And there were considerable arguments about this. When a man named Tycho Brahe got an idea of a way of answering the question, he thought that it might perhaps be a good idea to look very, very carefully and to record where the planets actually appear in the sky, and then the alternative theories might be distinguished from one another. This is the key of modern science and is the beginning of the true understanding of nature, this idea that to look at the thing, to record the details, and to hope that in the information thus obtained may lie a clue to one or another of a possible theoretical interpretations. So Tycho, who was a rich man and owned, I believe, an island near Copenhagen, outfitted his island with great brass circles and special observing positions, situation chairs that you could look through little holes, and recorded night after night the position of the planets. It's only through such hard work that we can find out anything. When all these data were collected, they came into the hands of Kepler, who then tried to analyze what kinds of motions the planets made around the sun. And he did this by a method of trial and error. At one stage he thought he had it. He figured out that they went around the sun in circles with the sun off center, and noticed that one planet, I think it was Mars, but I don't know, was 8 minutes of arc off, and he decided that this was too big for Tycho Brahe to have made an error, and that this was not the right answer. So because of the precision of experiments, he was able to proceed and to go on to another trial, and found, in fact, ultimately this. 3 things. First, that the planets went in ellipses around the sun, with the sun as the focus. An ellipse is a curve all artists know about because it's a foreshortened circle, or children know about because somebody told them that if you take a string and tie it to 2 tacks and put a pencil in there, it'll make an ellipse. These 2 tacks are the foci, and if the sun is here, the shape of the orbit of a planet around the sun is one of these curves. The next question is, and going around the ellipse, how does it go? Does it go faster when it's near the sun, slower when it's further from the sun, and so on? We take away the other focus, we have the sun then and the planet going around. And Kepler found the answer to this too.